Good morning, Calculus 1. I'm moving on into section 5.5, very important section. Last few sections here, chapter 5, are important and maybe a little more difficult, but we'll start. I can explain it to you, so don't worry. This one is integration by substitution. So section 5.5, integration by substitution. So you know this. We're back to some indefinite integrals here for a minute. The integral of cosine x, the antiderivative is sine x. Because, let me just check, the derivative of sine is cosine. Right, okay. The integral of e to the x is e to the x. That's easy because the derivative, let's see, the antiderivative, the integral of x to the fifth, that's just a nice power rule. 1/6 x to the sixth. Yeah, that's the power rule, because if you did a derivative, you'd bring the 6 down, it would cancel x to the, you'd get x to, yeah. So I did some antiderivatives, basic ones there, and I checked them by doing a derivative. Well, so watch what happens here now. I'm going to explain this, and then I got to explain this in layers here a little bit. So what if you had cosine 2x? Well, you might think the answer is sine 2x, and you'd be wrong, actually. I mean, I'd be right. Why is this wrong? If I check this, the derivative of sine 2x is cosine 2x, but the chain rule, when I do a derivative, there's a chain rule that spits out a 2. So the derivative of this is not this. The derivative of this has a 2 multiplied by it. So I could adjust. I could adjust somehow. Let's see. To get this to be the answer, I need a 2 right here, because the derivative of sine 2x is cosine 2x. Chain rule spits out a 2, so now the antiderivative of this is sine 2x. So what did I just do? I multiplied by a 2 to make that happen. So to compensate, to make that legal, maybe I'll go out front and multiply by a half. So now I have this answer is the sine 2x, but to compensate for that multiplied 2, I multiplied by a half, so actually there's a half out in front of this. Now that's not usually the way I explain it, but I'm trying to get you to think about sort of the reverse chain rule, so to speak. You know, when I first taught integration, I said there's these rules. This power rule is a big one, but there is not product rules, there is not a quotient rule, and there is not a chain rule. But there is this idea, and the book sort of talks and explains it like this, but I'm gonna end up doing it with substitution in a minute. Let's just try another one though. Let's try this e to the x a second. What if I had e to the negative 1/3 x? Again, if you just say, oh, that's the rule, okay, so the answer is e to the negative 1/3 x. That doesn't work. That does not work, because if you checked it and tried to do his derivative would be e to the negative 1/3 x, but the chain rule spits out a negative 1/3. So for this to be the antiderivative, I need a negative 1/3 right there. Now it's the antiderivative, but I just changed the problem, and to compensate for that, I think I'll go out front and multiply by a negative 3. So as you can see, I've multiplied by a 1. But I've made this fit the form where that is the antiderivative, and now there's a negative 3 out in front of it. So there's the answer. So I'm kind of backwards engineering the chain rule when I do this problem. I'm going to do one more with a power rule here. Watch this. If I have 2/3 x plus 8 raised to the 5th, you might say, oh, that's something raised to the 5th. Something raised to the 5th is that's something raised to the 6th divided by 6. I mean, that's just using a power rule. But hold on. If I was to check this, you'd bring the 6 down, you'd get this to the 5th, but the chain rule would spit out a 2/3, doing the derivative. So doing oh my goodness, hang on. So the chain rule would, so I would need a 2/3 right here for that to really be legal. For this to be the antiderivative, I would need a 2/3 there. To compensate for that manipulation I did, I'll better go out front and multiply by a 3/2. So this is the answer if you multiply by 3/2. Anyway, I feel like that's kind of complicated explanation. That is kind of the way the book explains it. Let me show you a little different way of doing it. What we learn is what we call U-Substitution. And so when they kind of give me these new rules, they say, hey, now you're going to integrate the cosine of u with respect to the variable u. And then the answer will be the sine of u. I mean, it's the same rule, but they use the letter u when the argument of the function is more than just an x. When it's just an x, it's just an x. But when the argument of the function is more than just an x, we use a u. So it's e to the u du. So it's a change of variable game. It's a substitution game. So let me just write these rules here. There are these new rules with u's in here. This is what they call the general power rule. If you have, I'll just write it like this. If you have u to the n, the general power du. Now it doesn't work. U to the n dx doesn't work. I mean, if the variable's u, you better have a du. It's a crucial part of this game. So anyway, then it's it's u to the n plus 1 over n plus 1 plus c. But now if I do these problems, okay, I'm going to get rid of them, but I might redo the same problems. If I have the cosine of 2x dx, then that was pretty easy the way we kind of reversed engineered the chain rule, but really this game is called U-Substitution, and I let u equal the 2x. And then that's going to be substituting in for u. And so if I do substitute that in, this becomes the cosine of u, and then this is dx, and that doesn't work. I mean, the variable changed to u, the dx has to change to du. But the dx is not automatically just du. Hold on. The relationship between dx and du is right here. If u equals 2x, what you do here is you take this derivative. The derivative of u is du, and the derivative of 2x is a 2 dx. Now that might look a little funny to you here. Let me explain a little further. If I took the derivative, you might say, oh, it's u prime and it equals 2. You could say that. The derivative, but what you're doing is the derivative of u with respect to x is equal to 2. And then you can sort of think about multiplying the dx over to the other side, which results in this. So the way we do this derivative is we just take the derivative of u and we call it du, and we take the derivative of this, which is a 2 dx. All right, so now I have the relationship between du and dx. So hang on, what is dx? I'm going to replace this. Remember, I'm doing substitution. I'm going to replace that dx. Oh, it's a 1/2 du. Okay, so when I replace this dx, it's a 1/2 du. If you don't mind, I'm going to call it du, and I'm going to slide the 1/2 out front. It's a multiplied constant. You can pull it out front. Hey, now you're integrating the cosine of u. What is the cosine of u? Oh, the sine of u with a 1/2 out front plus c. Problem over, except wait a minute, you got to get your u. This u substitution was a temporary variable. We need to get back to the original x's. So what was u? It was 2x. So the answer is this. And that seemed like a long, complicated explanation. I'm sorry, I'm explaining this as best I can. It's a process called U-Substitution, and it allows you to do a lot more integrals than you used to do. You can do anything of the form e to the u now. You can do anything of a form u to the n now. But you should go through the steps of U-Substitution. You might think that first way I explained it was a little easier. And you might be right. But for a simple problem like this, you might be right. But I want to explain the steps. I think for more complicated problems, we need the process of U-Substitution. This is what I'm trying to, you need to learn this process. And writing it down. And there comes a point where maybe you get kind of good at it, and for these simple ones, you can do it in your head. Listen, I know what's going to happen. I'm going to get the sine of 2x, and it's going to spit out a 1/2. Why does it spit out a 1/2? Well, because of this U-Substitution. Let's do another one. Let's do, we had this, what did I have? I think, I had 2/3 x plus 8 raised to the 5th. All right, I want to do the U substitution. I'm trying to make it fit the general power rule. So what do you think U should be? Sometimes there's a debate on what you should call U, but I think I should call U equals what's inside here, the 2/3 x plus 8. So then when I replace this, I'll have a U to the 5th. All right, but hang on, be careful. After you call U something, I think the very next step is you better find out what du is. So du is the derivative of u, du. The derivative over on the other side of a 2/3 x is a 2/3 dx. Remember, the derivative of 8 is 0. Okay, so now wait a minute. What's dx? If it's 2, I want dx by itself. So I like to divide by this 2/3 or multiply by 3/2. Du is equal to the dx. And now I replace all this stuff. I'm going to erase this if you don't mind. I'm going to replace this. This integral becomes, hang on, what is it? Oh, u to the 5th, u to the 5th. And what does the dx become? There it is. It's a 3/2 du. But it's a multiplied 3/2. I'd like to slide it out front like a constant. And so there it is. It's a 3/2 u to the 5th du. Now you've done all that work, but you haven't integrated yet. We need to integrate. It's a power rule. It's 1/6 u to the 6th plus c. Don't forget there's a 3/2 in front of that, and there's the answer. Also, don't forget, you don't leave it like that. You need to put your u back in there. You need to get back to the original variable, which was x. I'm going to do a little cleaning on this here. I think that's going to be a 1/4 when I clean that up. 3/12, yeah. And then this is my 2/3 x plus 8 quantity raised to the 6th. So there's the answer. And there's the process. It's a process called U-substitution. All right, I got a lot more to say about that, more examples, but I'm going to hit pause now.